morning, everyone. Okay, so some update about this digital control course. We are at I think it's under the final stage. Right now is today will be May 16, the 30th week that I upload. I think the handout number 6, I may have a last handout number 7 to upload. Week 30, I am going to finish the closed loop controller design method number 1 and method number 2, hopefully. And next week, May 23, from the original schedule, I'm going to introduce the DB control, which is a modified version for method number 2. So I upload 2 handouts. I'm going to use these 2 handouts. The first one is the handout number 5 on week 10. So it is related to the raw Lucas design. Next week, I have already finished the method number 1, and today I'm going to use this raw Lucas to analyze our linear approximation accuracy. So if you have some memory from last week, in continuous time, we should be able to achieve the post-zero cancellation, which means we should not have this underdamped property. So we will check our controller based on the raw Lucas analysis today. So I am going to review some of the controller we finished last week. And for method number 2, we are going to directly decide in digital domain. So I'm going to use the process my advisor teach me 10 years ago. This is called the direct design process. And I also upload the same handout, here. I'm going to use these methods to design the same current like the electrical circuit with iron load using this direct design methods. And some change about this course. As I said, the week 14th, it should be the last course for the closed loop controller design. And I'm going to introduce some advanced closed loop control. And for the last week, which will be week 15th, the last year, I show you the common feed forward, and this is the video lecture I guess last week. So I'm going to do some change this year. For week 14th, since we are at the final stage of the semester, so this year, give you guys a little bit relaxed. I invite one industrial people from Delta Electronics, and he is a product manager. So last year, I asked this industrial partner to introduce you the data center. Some motor drive or the power electronic system like UPS or energy storage used in data center. The high performance computer data center. This lecturer, his background, he is on the UPS. UPS means the energy. I forget the full name. UPS. I will check it later, but this is the energy storage. When our electricity shut down, he can provide some electricity for all the building. It's called UPS. Actually, TSMC used a lot of UPS in their factory. So he said this lecture next week will be 1 hour to 90 minutes, and he invited his colleague to present something in the data center related to the Delta Electronics business. Delta is I think right now it's a very famous company in Taiwan. Actually worldwide, all the world related to the energy storage. I think it will be interesting for you guys. So for next week, I asked them to come here at 10. So I still have 1 hour to finish our closed loop controller design. And if something I cannot catch up, I am not able to finish, please watch the video online, or as you should watch which video. This is the course related to May 23, but sorry for international students. The Delta, my friend in Delta, he said he can only speak Chinese, even with the English presentation material. But fortunately, this is unfortunately, I talked with some students from my lab. He is going to, and the TI, they are going to give you a real-time translation, including me. So anyway, the presentation material will be in English, but I will ask him to speak some keyword in English, maybe in German. I don't know if he can speak German or not. So it will be an interesting guest lecture for you guys. I hope you can have a great feedback, great memory for this course. So for next week, I'm going to change this as a guest lecture. So in this case, you may need to watch some videos because I may not be able to spend all the 3 hours next week for you. Next week, sorry, I have something in Japan similar to last year. So next week it will be online lecture. The last week in May, similar to last year. I'm going to Japan. Okay, related to the final, the first week in June, I just discussed with TA. Hopefully, you should be able to hand in the project number 2 on the last week of in the May, related to project number 3. I'm thinking about I am going to release the project number 3 in week 15th, but you don't need to hand in the project number 3. But something to encourage you to understand project number 3, some question in project number 3 should be appeared in final exam. I'm thinking about this, so for next week, I will spend some time to talk to you about the project number 3 and the final exam. The final exam should be partial of closed-loop control design and the partial of project number 3. But you don't need to actually prepare the hard copy report for project number 3 at this time. Okay? So let me know if you have any question about these 3, including this week. The last 3 weeks, like a course material. And with that, next week will be our very famous industrial symposium called Computex in Taipei. A lot of AI technology, technology, high performance computer, IC design, robot, and data center. They are going to release from this Computex conference. So I encourage you to join this Computex conference in Nangang. If you take the Metro Blue Line, the last stop, the outbound, I think this is Taipei. We are here, this NTU. Computex conference is here. So it should be eastbound. Eastbound outside the city, the blue line. You should be able to join the Computex. I checked this morning, you have to register. You have to register in order to participate in this Computex conference. If you don't know how to register, you can contact me. I am a special number for Computex, so I can send you the invitation later. In this case, you don't need to register. I will give TA, and if you have trouble, you don't know how to register the Computex conference, you just use this electronic invitation letter. You should be able to enter inside this conference. Actually, this is another company sent me this invitation, but it can be for anyone. A lot of famous people, they said that they will join this Computex conference symposium. It's called Computex symposium, including Rensen Huang. Rensen Huang is I think he has arrived Taiwan yesterday with his family. The NVIDIA CEO actually is a Taiwanese American. He said that he will give a seminar in this Computex. And what else? Who else? The AMD CEO, Intel, the new CEO. Intel new CEO, I read the newspaper, he said he will be in Computex conference as well. So it's a very good time for you, Computex conference. But don't go to Computex conference on Tuesday. Next Tuesday we have a Delta seminar. Toyota seminar Tuesday. So it's all the week, I think. Okay?
Sorry, Tuesday or Thursday?
Oh, sorry, Thursday. Remsen is, he will be appeared. I don't know because if he appeared in Computex conference, it will be very cloudy. So he didn't release any news when he will be in this conference, but I think on Tuesday. I think it's Tuesday. Okay. All right. So I'm going to use this handout. I'm going to use this handout later. And with that, I need to review something. You see, computer control delay. I push 3 times button. This is related to the delay during the computer control. All right, I think I can finish. I hope I can finish the closed loop control today. Let me close this. So the last review, you have to learn two methodology to design a closed loop control, especially in final is that 2CZ. Right now you should have some knowledge for the closed loop control design. This is called a closed loop digital controller. Two controller design methods. Okay, so CZ right now is our controller. The input is our error reference signal in digital domain. With our command, our tracking command, and our measurement. Our measurement, the E value. For the open loop control, the manipulated input is decided by ourselves. For digital control, for closed loop control, the manipulated input will be decided by our CZ, closed loop controller. So right now, all the things on the left-hand side, you should be able to implement in digital domain in computer, including zero order hall, A to D, and analog to digital converter, closed loop controller. The purpose is to control this dynamic system we call the GS in continuous time. Okay? I have already shown you the first one. The first one is called a continuous linear approximation. In short, we can call this as the continuous approximation. Okay, second one. second method, which I'm going to show you today, on handout number 6. Number 6. The red Z-domain design. I'm going to give you some comparison between these two design methodologies. The first one, continuous approximation, is under the assumption Z is equal to exponential st, and t is close to 0. Only this assumption appear, the continuous approximation can be used. So the key limitation should be you have to have a high performance computer system. This is why you guys need to join Computex next week. You can understand the state of the art, cutting edge, high performance computer like a GV300. Last year it's called a GV200. This year called GV300. The computing power is beyond 1 megawatt for AI. AI is a very high performance computer system. Okay. So if you are not familiar with high performance computer, you may need to consider the second method called direct Z-domain design. In this case, you don't need to consider the B to A and the A to B interface, which is the sample time. As I continuously emphasize, the difference between continuous time and the discrete time is D to A and A to D. The key parameter inside D to A and A to D is sample. First one as a sample time limitation. Second one is independent relative to any sample time. So with that, I'm going to verify why the sample time is limited for continuous time approximation. So let's go back to our original question last week, which is the IO load circuit. IO load circuit. So actually, I just write the block diagram directly. So the block diagram will like this. IO load circuit is relative to a first order system. This is the first order system 1 over Ls, and the input is the voltage. Output will be a current. This is L. However, it has R. R will introduce a nonlinear, internal feedback, non-zero internal feedback. So our load circuit is relative to a first order system, similar to the pure integrator system, but it with non-zero internal feedback. like this. Okay, so for continuous approximation, the method number 1, the first step for method number 1 is, what's the first step? Decide a CS. So we all know that non-zero internal feedback. What type of controller we are going to use? Non-zero internal feedback. If you use P control, you should have a steady state error. So you have to add an additional interval control. So we decide CS here, CS in continuous time using PI control. So it should be KP plus KI over S. Okay, I control meets the steady state requirement, no steady state error. No steady state error. The purpose for closed loop control is both to improve the steady state performance and the transient dynamic performance. For steady state, the minimum requirement, no steady state error. How about transient? Transient is related to your parameter selection, so it will have a bandwidth requirement. In this case, we have to modify our PI controller based on this. And for this controller, the overall transfer function based on the Mason's principle is related to 1 over LS plus R. So it has the pole related to minus R over L. From Lucas. This is an open loop pole location. Okay, so how to decide this PI controller? How to decide this PI controller for transient application? For major of mechanical system, we don't like the oscillation. So for me, I suggest you to decide this as the overdamped system. So I will use the technology I explained last week called the pole zero cancellation. From your automatic control, the requirement for pole zero cancellation is to make sure your open loop pole and the zero should be in the stable area. So right now this is minus R over L. This is a stable system, so we should be able to apply a pole zero cancellation. For this PI controller, it contains a zero. Is equal to minus Ki over Kp, and the pole S is equal to 0. This is the controller pole. And another 0, so we just apply a pole zero cancellation to make sure this is the overdamped system, which is this is 0 should be equal to minus R hat over L hat. Using hat to denote this parameter is the estimate parameter. We didn't know the actual condition for in the real world. So you use R, you can analyze the parameter sensitivity later. Next issue, for this pole zero cancellation, if you directly decide a zero in this area, you can only have 1 radial per second bandwidth because the overall transfer function will be equal to s plus 1 over 1. So in order to overcome this issue, we added another single parameter called K outside this controller. And we can adjust this K for any bandwidth we want. So actually the controller will be like this. So it's equal to, we can reformulate based on the PI format. So if you want to reformulate as the PI format, it's equal to K L plus RS. Okay? Then step 2, find the CZ. Find the CZ based on 3 linear approximation. Which one you prefer? For me, I prefer to use bilinear. Approximation. Based on the average process, bilinear can give us a better performance when t is not close to 0. You are going to compare this for your project. So what is the relationship between S and the Z for bilinear transformation? For domestic students, and I wanna give you the ratio between S and the Z for these 3 approximation methods, because you should be able to find that. Within 1 and 2 minutes based on your high school math skill. So for bilinear, is equal to 2 over t, 1 minus z minus 1, 1 plus z, 1 plus z minus 1. Okay, so for this PI controller, T no S appeared for our P controller, so we just need to modify the integral controller. So I also show you 3 different approximations for integral and the differential controller. So for integral controller, you can write this as to inverse this function, 1 plus z minus 1, 1 minus z minus 1 over R. Okay, so this is the controller. We decide in Z domain. Step number 3 is implementation in computer. If you want to implement this controller, you have to convert Z function is a usable tool for us to decide a closed loop controller like this. You don't need to do the convolution, and you can easily do analysis the stability. But for actual implementation, you have to find a difference in equation in K domain. So you have to do the inverse Z transformation. I'm not going to show you. This is not my objective today. Today, I'm going to analyze the linear approximation accuracy. So as we see, in continuous time, the bandwidth. The bandwidth should be here. This is our actual bandwidth. And this point is related to minus k. In here, k is equal to our bandwidth. The unit should be radian per second. Radian per second. K is equal to our bandwidth. And also, for any k, this is always the overdamp. This is always an overdamp system for any k design. In this case, this means with the PI control and the pole zero cancellation, my closed loop system will not have the oscillation property. It is always the overdamp system for any k in continuous time. How about discrete time? How about discrete time? So from our raw Lucas knowledge, this is called the S domain raw Lucas phi G omega. In discrete time, this controller, all the closed loop system should be inside this stable area. This is called a stable area. More importantly, overdamp system in discrete time, which means our closed loop controller pole should be located in which region? Overdamp. In discrete time. The pole should be from 0 to 1 in this region. Okay, so we can right now to check our controller design performance actually in discrete time, not in continuous time, because this is just called linear approximation. So for the overall discrete time system, is similar to that one. We have a controller CZ. Right now the input will be our current command, controller input, current arrow, based on the comparison between our command and the measurement. Output of this CZ manipulate input NK. The open loop system in continuous time, this is called GS. In discrete time, before the midterm exam, we use another system called NSDZ to define this open loop system. Output for this NSDZ is IK. This is CZ. So from this break, can you show me why is the corresponding NSDZ. You can just use the Mason number 2 is equal to the Z transformation of zero order Hall S times GS. So it's equal to the Z transformation, the zero order Hall S domain transfer function times the GS. You calculate this, CZ is here, the overall closed loop transfer function, TZ is equal to the output IZ and the I star Z. And then you can investigate the pole location for this TZ to see if this is overdamped system or not. Okay? Let's take a break. I'm going to show you the difference between continuous time and discrete time later. Okay? Thank you.